This is a video for AP Physics introducing power and the beginning of electric circuits with an introduction to EMF. We talked about power before. Power can be defined as the rate at which work is done, okay, or the rate at which energy is expended or converted or dissipated. Basically, anything you have where it's joules per second. So the wording can be different, but if you're in units of joules per second, which is a watt, then you're referring to power. So then kind of base level understanding of power, we can give it as work over time or energy over time. Work or energy, we can use our definition equation for voltage, which was V is equal to work over charge. Solving down for work, that's Q times V divided by delta T. Looking at the ratio then of Q over delta T that shows up, that is electric current. So substituting that in, we get power is V times I. That's the electric potential times the current. With a couple of substitutions from V equals I times R, we can write the power equation in three different forms, and we'll use whichever of those is convenient based on what we know. Now, a little bit more background on circuits and circuit elements. Resistors can be found in circuits, and we will find a time to be able to pull out some circuit boards. Resistors have color bands on them, and each of those color bands represent a certain number. So if you hold a resistor with a metallic band towards the right, then you have three color bands. The first one represents a digit, the second one represents a digit, and the third one represents a multiplier. This is a summary of what those numbers mean. Okay, with the first one representing a digit, the second one a digit, the third one a multiplier. And so the green, blue, yellow would represent a 5, then a 6, and then the yellow represents a 4, and so that 4 is 4 zeros that follow. So 560,000 ohms or 560 kiloohms. The metallic band is a tolerance. Tells you the accuracy of that value. We won't use that for too much. Now, more specifics on circuits, getting into chapter 28. A battery. A battery is a source of a voltage or an EMF that we'll get into in more detail. Remember, inside of a battery, there are chemicals. There is a chemical reaction. In that chemical reaction, one of your electrodes, which in this case would be the carbon rod that runs down the center, reacts with the second electrode, which would be your outer cup that goes around the sides. There's an electrolyte paste between them, so that reaction occurs at a distance, basically dissolving that center carbon rod through the paste, transferring charge to result in stripping electrons off of one electrode and depositing them on the other electrode. When a battery dies, you have completely dissolved that central rod away. So then when you have a battery that is rechargeable, then that chemical reaction is reversible. So then that reversed chemical reaction rebuilds that central rod so that you can use the battery again. Some chemical reactions are reversible, some chemical reactions are not. A different shape battery has a different geometry to it, but it's still the same basic idea. EMF. EMF is an old term that is still used. Originally, a battery was thought to be a device that stored force. And so when you used it, it delivered a force to be able to motivate charges to move. The electromotive force, motivating charges to move. And that is not the current understanding of what a battery does. A battery delivers a voltage. However, the term EMF has continued. Now, I want you to do a little experiment. I have left bulbs, batteries, battery holders, light bulb holders, and then the alligator clip wires up on the front board. And the digital multimeters over there on the counter. Turn the digital multimeters, the gray ones, to a setting of DCV, DC volts, 10 volts. First thing I want you to do is to measure the voltage on the battery by touching the probes to the two terminals of the battery. Okay, one is on the top, one is on the bottom, and measure the voltage across that battery when it is not in a circuit. This is known as the open circuit voltage, or the EMF. EMF symbolically is abbreviated with a fancy looking E. So measure that EMF, that open circuit voltage of the battery. Then I want you to set up a circuit with the battery that illuminates a light bulb, that lights up a light bulb. And when that circuit is running and that light bulb is lit, then I want you to measure the voltage in the circuit again. So that's when the battery is actually running, and then compare the terminal voltage measured when the light bulb is lit to the EMF. Pause the video here and go do that. Now, hopefully what you recorded were two different voltage values. If you used a single battery, D cell battery, they are published to have 1.5 volts. I'm going to assume that when it was not in a circuit, maybe you measured a value like 1.56 volts, a number a little bit higher than 1.5 volts. When it was running in the circuit, you should have measured a little bit lower voltage value. I'm going to assume a value somewhere in the neighborhood of about 1.5 volts. So you actually have a higher voltage when the battery is not operating. This is due to something called internal resistance. In other words, a battery has chemicals. A battery has terminals, which are made of conductors. And when there is no charge flowing, there's no resistance to charge flowing. And so you get a higher value for the voltage. When you actually have the chemical reaction occurring, then charges are flowing, and there is an internal resistance that actually converts some of the energy of the charges into heat energy, causing the voltage that is actually delivered to the circuit to be less. So that internal resistance is due to the materials that the battery is made of, and when the charges are flowing, there is a resistance associated with the battery itself. Ideally, that resistance is very low. Okay, so then we will deal with ideal batteries and real batteries. Ideal batteries, that internal resistance is essentially zero. So then the EMF matches the terminal voltage, or the voltage delivered to the circuit when things are running. In a real value, that internal resistance has some value, typically very small, and so you're going to deliver a voltage to the circuit that is a little bit lower than the EMF of the battery. Now let's consider an example. We have a D-cell battery of voltage 1.5 volts used to light a bulb of resistance 50 ohms with a current of 0.027 amps. Calculate the internal resistance of the battery. First of all, let's diagram the circuit to represent an internal resistance. We would have a battery. I'm going to leave a little bit of a space there. We would have a bulb, which would have a certain resistance. So this squiggly line is a symbol for a resistance. So this resistance value would be 50 ohms, and this would be our bulb. You have an internal resistance. When internal resistance is generally drawn as a little resistor on a diagonal, and so then your battery would be this entire section right there with an internal resistance. So our EMF is 1.5 volts. Part of that voltage would drop across the internal resistor, lowercase r. The rest of it would drop across the bulb. We've got a current of 0.027 amps. Okay, so then if we use Ohm's law, V is equal to I times R. We know if there's an internal resistance, our circuit is going to have more resistance than 50 ohms total. So then if I plug 1.5 volts in here and my current of 0.027 amps, and I solve down for the resistance, then I'm going to get a value for that resistance of 55.56 ohms. This resistance is actually the internal resistance plus the bulb. So that means our plus R of the bulb, so then our internal resistance of the bulb would be the difference minus the 50, or about 5.56 ohms. We will kind of summarize and bring things together with circuits next time I see you.